So Unit 9, Lesson 2, Part 3, guided notes here. We're still talking about the 2-sample t-interval for the difference between two means. We've already talked about the conditions that need to be met, and then we talked about the components that make up this formula. We left off talking about the degree of freedom. So there's the complicated way, especially if you are a person back in the 1940s where you did not have a high-powered calculator, or you have the way that sometimes makes your interval larger than it needs to be, but it will be good enough. So it's just the conservative option. We will go through what happens when you do both of them and look at the difference in our intervals, but we talked about this was our setup for it. So we're going to go back to example 1, which was talking about those 1-bedroom and 2-bedroom apartments. We already checked the conditions, and this has already generated excuse me, the summary statistics. So I'm seeing sample size, means, standard deviations, and then the 5-number summaries. So I'm going to go ahead and talk about the degrees of freedom and our critical values and the intervals. Now, I did, out of curiosity's sake, try to see if I could use that god-awful formula to find the degrees of freedom, and I was able to type it in. It is humanly possible, but it was less than pleasant. So the other option you have is if you go to your tests, so the same place we found all your tests and all your intervals, we are currently doing an interval, but we are doing a 2-sample t interval. I didn't enter the data into L1 and L2, so I'll have stats highlighted. And I'm just going to enter in the stats that are on your notes. So it was calculated that the mean of the first sample was 531, and its standard deviation was 82.792 from a sample of size 10. The mean of our second group was $609. The standard deviation of that was 89.312. And again, sample of size 10. And we would like to create a confidence interval that has a capture rate, essentially 90%, if we repeated this process with lots of samples. Then it's going to ask pooled or not. Now, we are essentially pooling together this data. Let me make sure I'm not lying to you on this. I lied. Pooling applies to something different that we're not currently talking about. So I think it should start out highlighted on no, leave it on no. So I'm going to hit calculate, and it spits out the interval of negative 144.8, negative 11.2. So this is the average difference of 1-bedroom apartments minus 2-bedroom apartments. So we're getting a negative number, which is telling us that on average, the 2-bedroom apartment is more expensive than the 1-bedroom apartment. So again, if I'm just using my calculator, I can go ahead and just say that's the interval I got. If we used option 2 instead, we would be taking each sample size and subtracting 1 from it. These happen to be the exact same sample size, so we don't have to debate which one's actually smaller. We're just going to go ahead and say 9 would be our degree of freedom. So you could go to the t distribution table, or you could use your calculator's inverse t option if it has it. If 90% of the area would be in the center, that leaves 10% in the tails. Half of 10% is 5%. So if I put this information into my calculator, which I haven't done yet, give me a second. I get a, oops, I don't need to write it there. I'm getting a critical value of negative 1.833. So as always, critical values are positive. So it spits out the negative, we'll just use the positive. So when I go to substitute this information in, I'm going to start with my sample statistics. So the difference in the sample means, that would be off the summary data earlier, 531 and 609. We'll be adding and subtracting that 1.833, and then multiplying by the standard error of our sample statistic here. So what was our standard deviation? 82.792. You can already see why it would be much more preferred to just plug it in your calculator and get an answer out. However, it can be done this way. So our point estimate is already negative. Our margin of error turns out to be about 70.591 if you put that on your calculator. which means I'm getting negative 148.591 up to negative 7.409, which you'll notice is not the same as this, but it's because this one is wider and we used a more conservative multiplier than we would have for this one. Here the multiplier was 17.898. Here, sorry, my degree of freedom was 17.898. If you use an inverse t with that degree of freedom instead, I don't remember what you get. You get negative 1.734. So it takes this critical value and shrinks it down to 5-ish, I guess, technically. So it shrinks your critical value, so it shrinks your confidence interval overall. So that's why they're different. It's not really a big deal which one you use. Just be clear that using this state with this degree of freedom, here is my interval, or with this degree of freedom, here's all my work to get my interval. You have to do one of the two. Don't just kind of say like, okay, well, here's this interval. I'm not going to tell you how I got it. It's magic. Don't do that. So it is wider. Option 1 has more degrees of freedom, more precise estimate, blah, blah, blah. So in example 2, just to kind of do a bit of review on describing the two different distributions, we always talked about the shape. We talked about anything that's abnormal that kind of sticks out as different or outliers, the center of the distribution and how spread it is, the variability of it. So I already typed out a bunch of it, or wrote out a bunch of it, because otherwise that'd get real boring. But we'll do the 4-step process in a second on this one. But it's talking about the Wade Tract Preserve in Georgia, an old growth forest of longleaf pines, survived in relatively undisturbed state for hundreds of years. One question of interest to foresters who study the area is how do the size of these pine trees in the northern and southern halves of the forest compare? So they took random samples of 30 trees from each half. They measured the diameter at breast height, which is denoted at dBH. They measured it in centimeters. And then they got these summary statistics from it. And they created these comparative box plots of the data. So we can already see some differences, which is what this first part's talking about. Just make a comparison based off the sample, and then we're going to quantify what we actually think is the difference between these in part B. So the shape. If we're talking about the shape of these, if I look at the ones in the north, we tend to have this area kind of condensed and not very different, whereas this half is a lot more variable. So I would say this one seems to be skewed to the right, but the opposite happens in the southern distribution. So here you got the spread outedness on the left, and the dBH is more concentrated on the upper end, on the higher values. So what that means is the distribution of dBH in the northern sample appears to be skewed to the right, while the distribution of the southern sample appears skewed left. So you'll notice I'm making a comparison. This does this, but the other one is like this, and I've put it in the context of the problem. I didn't see any outliers, so I'm just going to put no outliers present in either sample. If you actually talk about the center, one way we could do that is to compare their medians. That is one measure of center. The other way is to compare the mean, because that's calculated for us as well. Both measures of center are showing that the south has a higher center dBH value than the north does. So it appears that the trees in the southern half of the forest have larger diameters, because the mean and the median dBH for the southern samples are much larger than the corresponding values of the northern sample. So again, drawing direct comparisons between these two box plots. I think that was like I think it was unit 1 that we did that. It's been a while. So the variability, there's a couple different ways you talk about variability. But remember, that's just talking about how spread out it is. So you can see that the north spread outedness, the range would be higher for the north than it would be for the south, both in terms of just the range, but also in terms of the interquartile range. You can also look at the standard deviations that were calculated, and you can still see that all of them have the variability in the north turning out to be higher than the variability DBH value in the south. So there's more variability in the DBH of the northern longleaf pines. Pines, that sounded weird. So, and that's because we checked the range, the interquartile range, and the standard deviation. Whoa, that's not how you spell standard. So all of those are all larger for the northern sample. So we have some evidence that the south tends to have a higher DBH value than the north, but it has less variability than the north. We have all these things that we can say. So now we're going to create a confidence interval for the difference in these means. There we go. So the first step in our 4-step process is to plan. So I'm going to state what type of confidence interval I'm creating. So my plan is to create a 90% confidence interval, and I need to state what I'm trying to capture. So for mu sub 1 minus mu sub 2, ooh, and I didn't already write this out. Ugh, sorry. Where mu sub 1 is equal to the true mean if you're not already, you might want to speed this up to a 1.5 times speed, because this is not very quality content at the moment. Unless you're trying to write along with me. In which case, good luck, because I'm too lazy to write this twice. That's not the button I wanted. That is not either. Whatever. That's why I don't like writing these, just because it's so tedious to write nearly the exact same thing with a small deviation and a small difference, but to do it twice. But it is important to put it in context. If you're taking the AP test, don't skip that, because that's an annoying reason not to get your full points just because you're too lazy to do it. So then that's why. That's my state step. I didn't even do the state step. That's even more annoying. I'm not restarting this video. I've had to restart too many videos in the past 36 hours. I'm not doing this one. Actually, let's just move it. Make this a real mess for notes. Again, I should have started off with stating what I was about to do and then planning out my process. Trying to figure out what this is at the bottom. I think that's part of my ring revision. Ugh, what a mess. This is fun, I'm sure, for you to watch me figure out what the heck I was supposed to have done. I'm sorry. No turning back now, though. Whatever. Let's actually jump to the plan step. When you are planning, you are writing out what type of process you're about to embark on. We are doing a 2-sample T interval for the difference in our population means. I've already defined those variables, so I'm just going to write it like that. For the random condition, we need to go ahead and say independent. That's where that was supposed to go. Oh my gosh, what a mess. I'm going to jump to the 10% condition because I could tell for sure what I was supposed to put here. 30 is less than 10% of all trees in the northern half of the forest, and 30 is less than 10% of all trees in the southern half of the forest. That's much more obvious. If I'm talking about the random condition, I appear to try to have saved myself some steps here, but I don't know what I'm writing. Independent random samples of 30 trees, each from... Oh, this is so unprofessional. Here. Independent random samples. There we go. Just pretend like the past 30 seconds were flawless instructional strategies on my part. So we don't need to write that. Oh, it's late. I told you I don't do well after 9 o'clock. So we are talking about independent. We do need to state that because this was not, it wasn't an experiment, but we have independent random samples, specifically of 30 trees from these two different groups. Moving on, the normal large sample. So for this one, if they told us that the population was normal, awesome. I don't believe they did, but what they did do is they happened to take sample sizes that are at least 30. So I don't have to care about the distribution of the shape of our sample data. Doesn't really matter. Big enough sample size, the sampling distribution of the difference in sample means is going to be approximately normal. So for the do step, theoretically I should put that in my calculator. No, they already did that. Why do I have this written twice? It's probably good to be abundantly clear what you're about to use for your different data. So 34.53 is the mean, excuse me, of sample 1, because we've defined sample 1 as the southern half of the forests. So, excuse me, the table is a little kind of upside down if you're looking at it. 14.26 from a sample of 30, as was this sample. So this is the information I'm going to be using. You have two options. Option 1 is using your 2 sample t interval. So that would be just going to my calculator. Two sample t interval. I'm throwing in these stats of, again, 34.53, 6, sample size 30. Confidence level, we are running a, was it 90%? Yeah, 90% confidence interval. Just leave that alone. We'll talk about it later on in life. And we get an interval. So 3.9362, 17.724. That's what I could just go ahead and jump to. But I've stated how I got that. So it's not just this magic answer. It was through the magic of calculator work. But I do need to say what degree of freedom that is. Unfortunately, I just moved it off the camera screen. I'm going to go back. I talked about earlier. When it creates this interval for you, it does spit out that typically not a whole number degree of freedom value, the one that is the best, most accurate estimate for it. So I do need to state that this was built off of this particular degree of freedom. So you don't have to calculate it. The calculator will do it for you. So this is, whoa, using a degree of freedom of 55.728. So we could be done with the do step if we would choose. I am going to show you option 2. Not really sure if anyone would choose this, but theoretically you could be asked a multiple choice question, not on the AP test, but theoretically you could. My degree of freedom, both those samples were size 30, so I'm just going to use a degree of freedom of 29. using inverse norm of 0.05 and 29 degrees of freedom, or looking at the table, I get 1.699. So my interval would be the difference in the sample means, that's our point estimate for the difference in the population means, plus or minus our margin of error, which is found by this multiplier, times the standard error of our statistic. So we would be getting a point estimate of 10.83, plus or minus about 7. So we got 3.83, 17.83. Yeah, that seemed weird for a second. So again, close, should not pretty much ever be the same because the difference in that critical value. So we can conclude, again, this is the more precise answer, so I'll make my conclusion built off that. It wouldn't be wrong to use the other. But we're 90% confident that the interval from 3.963 to 17.724 centimeters captures u sub 1 minus mu sub 2, which is the true mean DBH difference of southern trees and northern trees. Now, one important thing to notice here, unlike that bedroom apartment one, we don't have negative values. We don't have negative values, and we also don't have 0. 0, remember, is the threshold of when there is no difference. So this interval does not include 0. Excuse me. Which means seems like there's a difference. It makes it seem like when I subtract these two numbers, it's not plausible to get 0. So we have convincing evidence that the difference in the mean diameter of northern and southern trees in this preserve is not 0. The interval suggests that the mean diameter is somewhere between 3.94 and 17.72. So that's what it seems like the difference is, somewhere between those, but it's not 0. So we would have convincing evidence, which will lead us into the next section when we're going to go back to hypothesis testing, but now for means.